All right, welcome back to the deep dive. Today, we're tackling a subject that, on the surface, feels incredibly technical. We're talking about servers, databases, memory management, but when you really peel it back, it's almost a philosophical crisis, just disguised as engineering. We have a stack of sources here, technical guides, postmortems, some architectural white papers, and they all point to this one single mechanism. It's the reason your Twitter feed loads in milliseconds, but it's also the reason why sometimes you click a flight price and suddenly it jumps $50.
It really is the invisible backbone of the modern web. And you're so right about the philosophical crisis part. The core theme, really, in all these documents is that to make the internet usable at the scale we have today, engineers had to make a very uncomfortable choice. They had to choose between speed and truth.
Speed versus truth, that is such a good hook. We are talking about caching. And the guide we're basing a lot of this conversation on calls it the controlled lie, which I think is just the coolest, slightly ominous name for a technical concept.
It's dead on accurate, though. A cache is literally a system that is designed to lie to you. It serves you a memory of the past because the present reality is just, well, it's too slow and too expensive to fetch every single time.
Okay, so let's start with the why. Why do we even need to lie? Why couldn't we just build faster computers and, tell the truth all the time? What's the original pain point here?
To get that, you have to look at the fundamental problem of early software scaling. You have your source of truth, usually a primary database. This is where the bank balance lives, or the inventory count for a shoe. It is precise, it is consistent, and it is safe.
Yeah.
But because it has to be all those things, it's slow.
When you say slow, we're talking in relative terms.
Right, exactly. We are talking maybe tens of milliseconds. To a human, that's instant. But to a computer, that is an eternity. And the real problem isn't just the speed of one request. It's the capacity. If you have a million users hitting that database at once, the queue just builds up. The source of truth is the tip.
The guide uses this restaurant analogy that I found really helpful to visualize this. It describes the database as the kitchen.
Yes. The kitchen is where the chef works.
Yeah.
The chef makes the risotto. It takes 20 minutes. It's made to order. It's fresh. It's perfect every time. That's your database. Now, the users are the customers. They are hungry. They're impatient. And importantly, they don't arrive in a nice orderly line. They come in bursts.
So if every single customer walks right into the kitchen and taps the chef on the shoulder to order,
The kitchen melts down.
Yeah.
The whole thing collapses.
reliability is gone. In software terms, the database CPU spikes to 100%, connections time out, and the site goes completely offline. So the solution is the waiter. The waiter realizes, hey, 50 people just ordered the tomato soup.
So instead of bothering the chef 50 times, the waiter just grabs a big pot of soup from the kitchen and keeps it at a station out in the dining room. Exactly. When you order soup, the waiter just hands it to you instantly from that station. The chef doesn't even know you're there. You get your food in milliseconds. That station? That is the cache. It's memory with permission to forget and, crucially, permission to be wrong.
Permission to be wrong. Okay, that's the part I really want to drill down on later because that sounds dangerous. But before we get to the danger, the notes mention that engineers didn't just jump straight to this complex caching idea. They tried simpler things first.
Oh, absolutely. The history of engineering is basically try the simple thing until physics tells you to stop. The first attempt was just vertical scaling.
Which is just buying bigger hardware.
Right. If the database is slow, buy a bigger server, more RAM, faster CPUs, faster disks, just more.
That seems logical. Why did that fail?
Moore's law, basically. Internet traffic grew exponentially. I mean, user bases for places like Facebook were doubling every few months. Hardware speed only doubles every 18 months or so. You literally couldn't buy a computer big enough to handle all that read traffic. You just hit a physical ceiling.
Okay, so you can't build a bigger engine. What's attempt number 2?
Database replicas. This is where you copy the kitchen. Instead of one database, you have 5 read-only copies. You send all the people who just want to look at data to the copies, and only the people who are changing data go to the main one.
This is standard practice now, right? I feel like I hear about read replicas all the time.
It is, but it has a flaw. A flaw that caching is specifically designed to solve: replication lag. Data takes time to travel from the main database to the copies. It's not magic, it's just data transfer. So you might update your profile picture, the write goes to the main database, but then you hit refresh.
And I'm reading from a copy that hasn't gotten the update yet, so I see my old photo.
Exactly. Users get confused. I just changed this, why didn't it save? Debugging becomes a nightmare because the system is essentially consistent, which is just a fancy way of saying currently wrong.
So that leads to attempt 3, which the guide calls local memory. This is where every application server just tries to remember things itself.
This is the every waiter has their own little soup pot approach. And it's incredibly fast because the data is living right there in the application's RAM. But it introduced what they call the Heisenberg bug.
I love that term. A bug that disappears when you try to find it.
Pretty much. See, since every server has its own separate memory, if I load a page and hit server A, it remembers me. It knows my shopping cart has 3 items. If I refresh the page and the load balancer sends me to server B.
Server B has never seen you before in its life.
Right, so my shopping cart suddenly empties. Or my login session just vanishes. Engineers learned a very hard lesson here. Remembering things randomly is actually worse than not remembering them at all. It creates this jarring, disjointed reality for the user.
That brings us to the modern solution, the distributed cache, the black box. Let's look under the hood. How does this actually work mechanically?
It acts as a shield. It sits physically between the fast code, your app, and the slow truth, the database. So let's walk through a request. Say you want to load a user's profile. The application first generates a key, usually a string like user.123.profile.
And it just asks the cache, hey, do you have the answer for this key?
Yes. And this is the magic part. It does a hash table lookup. In computer science terms, we call this an O1 operation.
Okay, unpack that for us. O of 1.
It means constant time. It means that looking up a piece of data takes the exact same amount of time whether there are 10 items in the cache or 10 billion items. It's basically instant. It doesn't have to search through a list. It goes directly to the address in memory.
Wow. That is fast.
It's blazingly fast. If the cache says yes, you get the data. The database is never touched. That's a cache hit. If it says no, a cache miss, then you have to do the walk of shame to the database, fetch the slow data, and then, and this is crucial, you save it into the cache for the next person.
But here's the thing I've always wondered. A cache is memory, usually RAM. RAM is expensive, it's finite, you can't just keep stuffing soup bowls onto the waiter's tray. Eventually you run out of space.
And that brings us to the most brutal part of caching, eviction policies. The cache has to decide what to kill.
What to kill? That sounds so dramatic.
It is. The system has to guess which piece of data is least likely to be needed again. The most common method is LRU, least recently used. The cache looks at everything it's holding and says, nobody has asked for this specific piece of data in 24 hours. Delete it. Make room for this new viral video that everyone wants.
It's like cleaning out your closet. If I haven't worn this shirt in a year, it goes to Goodwill to make room for a new jacket.
Exactly. And this highlights a crucial design constraint that developers just have to accept. Cache state is optional, it is losable, and it is rebuildable. If the cache loses data or the power goes out, the system shouldn't crash. It should just get slower for a little while as it rebuilds.
Okay, so we've got the mechanics, but earlier you mentioned the controlled lie. Let's get back to that. This is the trade-off section of our deep dive.
This really is the philosophical core. When you implement a cache, you are explicitly choosing speed over absolute correctness. You are saying, I prefer a fast answer to a guaranteed true answer.
That sounds really risky for a lot of businesses.
It depends entirely on the context. The guide offers a simple litmus test for this. You have to ask yourself one question. Is it okay if this answer is slightly old?
Give me some examples.
Okay. If you are looking at the number of likes on a celebrity's Instagram post, is it okay if that number is 5 seconds old?
Yeah, who cares? It's 5 million or 5,000,001. It doesn't change anything for me.
Exactly. So you cache it. Now, what if you are looking at your bank account balance right before you make a wire transfer? Is it okay if that is 5 seconds old?
Absolutely not. No way. If I think I have money and I don't, that's a huge problem.
Correct. So you cannot cache that. Or, if you do, the cache life has to be incredibly short, like milliseconds. The trade-off is you gain low latency and cost efficiency, but you lose consistency. You're offering probabilistic freshness instead of guaranteed truth.
Probabilistic freshness, that sounds like something written on a bag of salad.
And just like salad, sometimes it goes bad.
Which brings us to disasters, because when caching fails, it doesn't just break a little bit, it seems to fail catastrophically.
Oh, the failure modes are spectacular.
Yeah.
The most famous one is the thundering herd, sometimes called the cache stampede.
I love these names. What is a thundering herd?
Okay, imagine you have a very, very popular piece of data. Maybe it's the homepage of a news site during a breaking news event. It's cached, so millions of people are hitting the cache. Everything's fine. The database is just relaxing.
And then the cache for that item expires.
Right. The timer runs out. Suddenly, the cache is empty. Now, in that split second, before the cache can be refilled, 10,000 new requests come in. They all check the cache, they all see it's empty, and so they all decide to do what?
They all go to the kitchen. They all hit the database at the exact same moment.
And the database is instantly crushed. It is not designed for that. It's like a denial of service attack, but it's coming from your own users. The whole site goes down. All because one key expired at the wrong time.
That is terrifying. It's like a dam breaking.
It is. And then you have something called silent staleness. This is where the cache is never invalidated. So the source of truth changes. A price updates, a news story is corrected, but the cache just keeps serving the old version. Users are seeing a reality that doesn't exist anymore.
The source material had a really specific and painful example of this. It was about user permissions.
Yes, this is a classic horror story in the industry.
Mm-hmm.
A platform cached user permissions. Basically, can this user see this page? They deployed a code change that altered how permissions worked, but they forgot to clear the cache.
So the cache still had all the old permission rules.
Right. Users lost access to things they should have seen. But the real kicker, the admins tried to log in to the admin panel to fix it, but their admin permissions were also cached. And the cache said, according to my old list, you don't have access anymore.
They locked themselves out of their own building.
Because the cache was lying to them. The only solution was to flush everything, delete the entire cache, and take the massive traffic hit while the system slowly rebuilt itself from the database.
That brings up such a great point. Cache bugs look like business logic bugs, but they spread so much faster.
And they're a nightmare to debug because the data keeps changing on you.
So if the cache lying to us is the problem, we need to talk about how to stop it from lying. We need to talk about invalidation.
Ah, yes. The hardest problem in computer science.
The source material quotes that famous joke, there are only two hard things in computer science: cache invalidation and naming things. Why is it actually so hard? I mean, is it really that difficult to just say, delete this key?
It's not hard if you have one computer. If I write something down on a notepad and then I want to erase it, I just erase it. It's simple. But we're talking about distributed systems. Caching is local optimism. I'm assuming this piece of data is true right here for me. Invalidation is global coordination.
Global coordination.
Think of it like this. Imagine you need to shout an update across a crowded city and hope that everyone hears it at the exact same split second.
That's impossible.
Exactly. Some people will hear you instantly. Some will hear you a second later. Some won't hear you at all because a bus drove by. That is cache invalidation. You're trying to tell thousands of servers to forget something all at once.
So what are the strategies? How do people even try to solve this?
There are three main ways, and they all hurt a little bit. The first is time-based, or TTL, which stands for time to live. You just say, this data is good for 5 minutes.
That seems simple enough.
It is, but it means your data is guaranteed to be wrong for up to 5 minutes. If you make the time too short, you risk a thundering herd because it's always expiring. Too long, and users see bad data. Tuning that number is practically black magic.
Okay, strategy number 2.
Right through. This means delete when data changes. When you update the database, the app immediately sends a command to delete the cache.
That sounds logical. What's wrong with that?
Race conditions. In a distributed system, messages get lost or delayed. What if the delete command arrives before the new data is actually written? Or what if the network just blips and the delete command never arrives at all? Now you have stale resurrection. Old data just appearing out of nowhere.
Spooky. And the third one?
Versioning. You check a version number before you use the data, but this requires an extra round trip to check that version, which adds latency.
Which kind of defeats the entire purpose of caching to begin with.
Exactly. If you have to ask the database if the cache is still valid, you might as well just ask the database for the data itself.
So there's no silver bullet.
None. You just have to choose how you want to suffer.
And this gets even more complicated when we talk about big distributed systems. The distributive nightmare, as the guide calls it.
Oh yeah. Once you leave the world of a single server, you leave the world of shared truth. In a distributed system, there is no shared clock.
Wait, hold on. No shared clock?
Not one that is precise enough for this. And there is no shared memory. So server A might have one version of the truth in its cache, say, that a flight is $300. Server B has a totally different version, that the flight is $350. And they are both right according to their own local timeline.
That's mind-bending. It's like parallel universes coexisting.
It's just physics. You cannot have instant consistency across a distance.
So how do the giants handle this? How does a Google or a Netflix or an Uber keep it all together? They operate on a global scale.
They all have different philosophies. Google, for example, they just assume the cache will fail. They design their systems around it. They do aggressive pre-computation calculating answers before anyone even asks for them.
So they weren't looking things up. They already have the answer ready to go.
Exactly. And Netflix is interesting. They push the cache to the edge. They use CDN's content delivery networks to put the data physically closer to you, maybe in your ISP's data center.
So the movie thumbnail I'm looking at is living just down the street from my house.
Right. Netflix optimizes heavily for reads. They're willing to accept that the data might be a little stale. If a movie thumbnail is 10 minutes old, who cares? They prioritize the stream starting instantly over the list being perfectly up to the second.
Like Uber.
Uber is unique because a car's location changes every single second. Old data is not just old, it's useless. So they use location-aware keys and very short time-bound caching. If the data is more than a few seconds old, the system just treats it as garbage and forces a new lookup.
The source material mentions this cache-aside pattern. Is that what most normal companies use?
Yes, that's the same default. Your app checks the cache. If the data is missing, it fetches from the database and then it stores it in the cache. It accepts staleness, but it bounds the damage. It prevents the system from dying, even if the data is a little weird sometimes.
I really liked this concept of the hierarchy of truth that was in the notes.
It's a great mental model. Think of it as layers. Layer 0 is the CPU cache nanoseconds, incredibly fast, but tiny. Then you have local memory, then a distributed cache like Redis, then the CDN out at the edge, and finally, way at the bottom, the database.
And the rule is, the closer you get to the user.
The faster you are, but the less correct you are. The closer you are to the source to the database, the slower you are, but the more correct you are.
So architecture is basically just deciding where on that spectrum you want to live.
Precisely. You are deciding where to place the lie.
This has been such a fascinating look at something we just completely take for granted. We expect things to load, but behind the scenes, there's this massive coordinated effort to manage memory and forgetfulness.
It connects back to what the guide says in its outro. Caching doesn't actually remove load. It just reshapes it.
Reshapes it how?
It turns continuous, manageable pressure into sudden, violent spikes. That's the danger of synchronization we talked about. If everything expires at once, the system dies. So you have to be careful. You're trading a constant headache for the risk of a sudden catastrophic migraine.
So to wrap this all up, what is the final definition we should walk away with?
A cache is a controlled lie. The architecture of your system is just the decision of how dangerous you're willing to allow that lie to be.
That is such a cool way to put it. And the guide leaves us with one final, slightly provocative thought. It reminds us that almost everything you see on the internet, prices, profiles, news feeds, is likely just a memory of the past.
It's not the current reality, it's an echo.
And the memory anchor for today, the thing to stick in your own brain's cache, cache is a memory with permission to forget and permission to be wrong.
Couldn't have said it better myself.
Thanks for listening to this deep dive. We'll see you next time.
See ya.